over time, and
This time it's recorded in stereo.
what was it recording in last time?
Well, it has always been mono, which is the default.
Well, it should be recorded in mono. You're not going to get stereo separation in the classroom. We're just going to be able to tell where you are in the
exactly.
room based on...
See, now you can tell that I'm on this side, and now you can tell that I'm on the other side.
But what does that matter? It's just going to make it more confusing to those of us who listen to your lectures with one headphone in.
It does help to make people more disoriented spatially.
Yes, that's not a good thing. You realize that, right?
Oh, is that not a really good thing?
No, it's not. I'm going to start circulating a petition to bring back mono.
And because it's also recording at 44 kilohertz, it will record all the high frequencies too, which makes it even worse, because spatial disorientation mostly come from the higher frequencies. Lower frequencies are non-directional.
If anyone's using that unhearable ringtone, make sure it goes off during class.
Is it a ringtone? Well, in theory, you can sample all the way up to 22 kilohertz of actual audio signals.
Now see, if you were using 44 kilohertz mono, you could get it.
This is now 44 kilohertz stereo.
Yeah, which is half the frequency. See, you should have gone with mono. It would have been higher quality.
No, you cannot get any higher. That would not be possible.
Dude, my sound card supports 20,000 hertz. Wait, 20,000 kilohertz?
USB bus would be saturated also, I guess. Maybe.
Oh, I've got USB 3.
Alrighty.
You ready to
Well,
start?
let's get started. Are there any questions about the homework assignment? No questions? Okay, that's good. We can now proceed to additional topics. Okay, so let's go ahead and take a look. I can see that you guys have questions, even though you didn't say anything. Okay, how many people have tried to do it? At least, figure out a few cases. Okay, very good. Okay, the key is to get in and try to get it done as soon as possible, because the earlier you encounter problems, the more you think about it, the more it will sink in when I talk about the solution on Thursday. Now, I cannot talk about the solution, but I can talk about, how do you prove something is not possible or something that is possible. Okay, certain combinations of flags are impossible. Okay, what you need to do when you look at this homework assignment is not really to look at numbers as numbers. You want to look at numbers as ones and zeros, and then you look at the flags as logical output of certain operations. Okay, that's the best way of looking at things, at least from my perspective. What we'll do is we'll use a text editor to capture some of those cases first. So let's go use, gedit is good. Okay. We have already talked about the zero flag. What is the zero flag? Let's see. Let's take a look at a particular example. We have A, B, C, D. Each one. Okay, let's just try 2-bit by 2-bit addition. Okay, because this way we don't run out of letters easily. AB plus CD gets a result of EF, and here's my extra carry. GHI. Yeah, we'll just call it K. Okay. Okay, so this is a bit pattern, a general bit pattern. We are adding the input AB as a 2-bit input to the output of CD. K is the overall carry. In other words, if I want to write this out completely using the standard that we have been using up to this point, it will be the same as this. Okay? And the K bit is the one that has to end up here. All the other ones are internal. In other words, there may or may not be any ways for me to actually find out what these question marks are. Are there any questions about what is the notation of what we are talking about here? A is 1 bit, B is 1 bit. AB together is the first number in the addition. C is 1 bit, D is 1 bit, CD together is the input, the second input to the addition. The output or the sum are the bits EF. E is 1 bit, F is 1 bit. K is the overall carry, the carry that results in adding the most significant bits. Are there any questions about the notation, what this is representing? No questions? Okay. So when you look at it in the bitwise representation, the carry bit is the easiest one. The carry bit is basically our k bit. Okay? Any questions about this one? And it's not really that hard to make the carry flag either 1 or 0. Okay, so that one should not be a big challenge. The Z flag is not a big challenge either, because the Z flag is basically the negation of E and F. Is that making any sense? Is it E, F? I think E, let's see, has to be a conjunction. Yep, it's a disjunction, sorry, I take it back. Because if E or F, if E is a 1 or F is a 1, then the number is not a 0. I have to negate it so that the Z flag is 1 if and only if all bits are zeros. And that's why we have to use a disjunction in this case. Does it make any sense? What is the sign flag? The sign flag is a 1 when the number of the output is a negative number if we choose to interpret it in 2's complement. The sign flag is the most significant bit, and in this case, it is just the E bit. Are we doing okay so far? And there's only one flag left. What is the O flag? The O flag is the overflow flag. In other words, the O flag is a 1 if and only if the sign of the output does not make any sense. There are only 2 cases where the sign of an addition does not make any sense. If A, excuse me, let me turn that off. If the A flag is a 1 and the C flag is a 1, but the E flag is not a 1, then we have a problem. Right? Because you're adding a negative value to a negative value, but somehow the result is non-negative. The other way to get the overflow flag to become a 1 is when the A flag is, when A is 0, C is 0, and somehow E is non-zero, is a 1. So those are the 3 cases. So one way to represent that is to say A and C and not E. That's one case where the overflow flag is going to be a 1. This is basically saying the first number is a negative number because A is a 1. The second number is also a negative number because C is a 1. But somehow the output E is a 0. Okay? If all 3 components are non-zeros, or if all 3 components are 1 at the same time, then we have a problem because the sign of the output does not make any sense. Is that okay so far? The notation of this is a little bit different from the notes because I'm not using the over bar and the other symbols that I can use in the notes. And then we have another case where the sign cannot make any sense, which is not A, which means A is 0, not C, which means C is 0, but somehow E is a 1. That also does not make any sense because A being 0 means the first number is non-negative. C being 0 means the second number is non-negative. But if E is 1, that means the result is negative. So once again, the overflow flag should be set, which means it should be a 1. So this is the logic equation. These are the logic equations to come up with, okay, which bit or what equation do we use to come up with the result of which bit? Are we doing okay so far? And right away, I can see some of these are not exactly independent, okay? If you look at the Z flag and also the sign flag, they are not exactly independent. In other words, not all 4 combinations are possible because you can see that E is in the Z flag and E is also in the sign flag. So that gives you an idea of how you can prove whether it is possible or not. Okay? Now, this is easier to prove whether something is possible or not because you can spell out all possible combinations. Okay? Now, I don't really mean, B and D are inconsequential, so I don't want to deal with B and D. But E and F, okay, A, C, E, and K, these 4 bits are basically, there are only 4 inputs into the system. If you look at Z, it only involves E and F. So what you can do is to come up with a table. E, F, and then you have not E or F. Okay? E can be 0, 0, 1, 1. F can be 0, 1, 0, whoops, 1. Right? Because each one can only be a 0 or 1, and therefore you have 4 possible combinations of all the possible inputs. For each one, you have to figure out what is the end result of not E or F, okay? Which is not hard to do. You can even write a program to do it. I mean, this is something that you can do with a program. Okay, so now we have all 4 possible combinations for E and F. So what do? You also add the sign flag, which is just E by itself. And then you look at this table and you tell me whether it is possible for certain combinations to happen, and certain combinations cannot happen. And that's enough proof for me because you have enumerated all possible cases, and yet none of those cases can generate a particular combination of the flags. Are we doing okay so far? Yes?
I don't understand the last part.
Which one?
I don't understand the last part.
The last part.
When you say about E.
Well, E is just E here, okay? So the question is, when you look at the output of this column here, can you make it so that this column can be a 1 and this, can you make all 4 possible combinations? In other words, this whole thing is nothing more than our Z flag. Yeah, this whole thing is our Z flag here. So the question is, can the Z flag, and this one is nothing more than our S flag, right? So the question is, are all 4 combinations possible between the sign and the 0 flag? And the answer is no, it is not possible. Some of these combinations cannot happen. Because this table enumerates all possible ways to combine the E and the F flags, or the E and the F bits. And yet, some of the combinations are not possible. So you can prove by exhaustively listing all possible combinations of the input. If the input cannot generate a particular output combination, then it is not possible. Okay? Now this one can also be proved by contradiction, because you can say that, okay, let's say we can make it happen, okay? And then you can say, okay, and then you can use the logic to arrive to a contradiction and say, okay, but the outcome of this assumption is going to contradict with some of the assumptions to begin with. So people who have taken cisp310, you can try to flex your math proving, techniques in this class. I can see some people shaking their heads already. How many people have taken 440 at this point? Well, it's a good time to try to exercise, all those techniques that you learned about proof by contradiction. And
we also did that in linear algebra.
Linear algebra, okay. Now, this one is easier because, with Boolean logic, you can enumerate all possible cases. That makes things a whole lot easier. Yep.
So when we explain why something isn't possible, you want us to use this?
Yeah, you can use this, to prove that it is not possible. But there are certain patterns that have the same sub-pattern that you can prove that is impossible. If you look at a particular pattern, let's say the 4 bits, and the sub-pattern is known to be impossible, then the overall pattern is impossible as well. So that makes proving a whole lot easier because you can always say, refer to the proof in da-da-da-da, or just copy the text. Either way is fine. Okay? So is that helping or not? Helping a little bit? Okay. But in the end, it still needs some time. Okay, everything still needs some time because you still need to look at the equations this way. Because I just showed you the technique to prove it. I did not actually finish the proof, so you guys actually have to figure out what the question marks are in order to figure out. Oh, okay. So some of these combinations are not possible, and those are the combinations that do not show up in this table. Yep.
So, what is it going to be similar to for a 32-bit?
What? Sorry?
32-bit.
With 32-bit, that means you have a whole bunch of B's and a whole bunch of D's and a whole bunch of F's, but you still have the most significant bit A, C, and E, and also the overall carry of K. You see what I mean? You just, okay, when you have a 32-bit number, all you're doing is making the B really long, the D really long, and the F really long. But you still have a most significant bit for each number, as well as the result, and you still have an overall carry. Okay? The most difficult one to prove is when the carry flag is involved. Okay, certain combinations are not possible, but they involve the use of the carry flag, and those are a little bit more difficult to prove. But you can still prove it using this technique. Okay, any questions? Yep.
If it's a one, it means it's a negative flag, and zeros shows that it's not a negative flag.
Sorry, say it again.
I said if it ends in a one, it's a negative flag. If the K is a one, it's a negative flag. But if
No,
it's a
E
zero,
is the negative flag. E is the negative flag for the result.
So
And that's why we have the sign flag being the E flag in this particular notation. The most significant bit of the result is the sign flag of the result. Okay. Are there any questions at this point? Yep.
Where does the carry go?
The carry? The carry, there are two ways to set the carry flag. A, C being both ones can set the carry flag. But you can also have this carry from the previous calculation being a 1, and either A or C being a 1 that can also set the carry flag.
No, I mean where does it store?
Sorry?
Where does it store? In the
Where is it
program?
stored?
Yeah.
It is stored in the same status register as all the other flags. All 4 flags that we have talked about, they are all stored in what we call a status flag. In other words, the special properties after an addition or any calculation will be represented by flags, the 4 flags that we have seen here. And each one is a bit inside a status register. The status register has a name of E flags. If you look up, if you do an IR, you will see E flags as one of the registers. But using my GDB init file makes it easier because you don't have to interpret the bit pattern to find out which bit is a 1 and which one is not. Okay. Any other questions? No other questions? This is all good? Okay. Well, I'll still go to the lab. Oh, I messed it up, didn't I? I'll go to the lab later today, so if you guys have any questions, we can talk about it in the lab. But I cannot give you the answer. This is as close to the answer as I can get, which is pretty darn close already. And I will not, cheat and not save the file. So I'll go ahead and save the file first. And there we have it. It should be uploaded as soon as I get to the lab. Yep.
Can you give us an example of an explanation? Like what you want in the explanation?
The explanation?
Yeah.
Well,
Just
you
that
look
table and
at
then
just look at this
description.
table here and say, certain combinations of the S and the Z flags are not possible, even though all all combinations of E and F are examined. Then you can just say, nope, it's not possible.
So the table with the short description.
F is not important. It's the E flag that is important. Okay. You have to take this example and expand it to the numbers that you're dealing with, but you can use the same argument. In other words, if you're dealing with 32 bits, you don't have to spell out 32 items here. You can just use dot dot dot. Okay.
Regardless the off flags, right?
Mm-hmm.
The X, the off flag.
The what?
When the flag is off, is that those?
The lowercase x is when the flag is 0. Yes. Okay. Any other questions? I mean, you can use any argument, to convince me that a particular combination is not possible, but it has to be a reasonable explanation. Yep.
I'm sorry, if you don't mind, can you do an example? Because my English is not good.
I cannot do an example of a proof because if I do an example of a proof, then it is the answer. I can do an example of something that can happen, which is something that we did last time. Because if it's not possible, then the only thing you have to do is to prove it. If I prove it in the class, then you don't have anything else to do for those particular cases. Yep.
Yes, could you do like an example not having the same proof but the same reasoning?
The same
way,
reasoning.
Yes, the same way of thinking, the same methodology.
Let me think of one. You had a.
Yes. Can we prove it by exhaustive search?
Well, since it is a finite space, yes, you can, but that's going to take up quite a bit of space, wouldn't it, in the text file?
I've got 4 cores on my CPU. I could compute it and provide you a summary result.
That would not be a preferred way to prove things. Yep. Because the rationale behind things should be fairly easy.
Aww.
Yep.
Never mind, because I'm actually listening. You still can't do it because it's asking for another example.
I cannot do an example. I cannot use an example for the proof, but I can use an example on something that is possible.
Oh, can I see an example of something that's possible then? Maybe that might help.
Yes, you can, because that would be pretty easy for me to do.
Excuse me, should our example be in binary or hexadecimal, or it doesn't matter?
If you can make it work, it doesn't matter what is the number representation. So you can use hexadecimal, you can use decimal, you can use signed decimal, you can use unsigned decimal. It's entirely up to you to specify how you represent the value represented by the 32 bits. Yep.
Can we do binary?
Sorry?
Can we do it in binary?
You can do it in binary. I believe binary is 0T and then a whole string of zeros and ones. But then you have to count the zeros and ones, so I'm not sure that's the best way of doing things.
Just copy and paste 30 zeros and just put the 1 in. Sorry, 31.
Could do something like that.
I'm gonna have GDB do it, then just copy and paste it back into the code.
Well, you guys can use those techniques. It
Use
may
the
or may not
Ubuntu
be
calculator
helpful.
and convert to binary.
You can use calculators. You can use the built-in calculator of Windows to do it too.
Windows has a programming mode on it. Windows has a programmer.
No, you don't need it to be programming.
If you want it in binary, you do.
No. Okay, so here we
Perfect,
have
it does,
an example
awesome.
from before. Okay, so this is the note from last week. Okay, this is the note from last Thursday. And here is an example of setting the Z flag, clearing the Z flag, setting the sign flag, clearing the carry flag, and also setting the overflow flag. So it's already done. Here's an example.
Can you run
Yes.
this program? Can you run this?
Can I run this program? What program?
Like put it inside the program? Like I want to see how does it work.
You mean this case here?
Yeah.
You just have to sign extend it to, to the number of bits that you need. Yep.
Can we modify your program slightly to use like EH or EL and just use add n
Yes,
for
you can.
adding nibbles? Would that be
Yes.
acceptable?
Yep. Yep.
Does assembly support adding nibbles?
I do not know. You have to figure it out. Okay. So, but does it make sense? Okay. The question here is this making any sense? I have a 4-bit number, 0, 1, 1, 1. I have another 4-bit number, just 0, 0, 0, 1. I'm adding these two. Now, when I add numbers, I'm only using the 4 rules that we have talked about. 0 plus 0 is 0 with no carry. 0 plus 1 is 1 with no carry, and so on. So there are only 4 rules to adding. So in this case, when I'm adding, I'm looking at this one here. 1 plus 1 is a 0 with a carry. Okay? And this 0 is just always there. Then we have 0 plus 0 being 0. So that mechanism we have talked about already, and we should all know the mechanism of adding. Okay? So the question is, why is the z flag being 0? Because I'm taking an OR of all of these and taking the negation of that. What is 1, 0? What is 1 or 0 or 0 or 0?
1.
It's 1 because at least one of those things is a 1 and the whole thing is a 1. That's an OR. What is not 1?
0.
It's a 0. That's why the z flag is a 0. Okay? Why is the sign flag a 1? Because it's the most significant bit of the result. Why is the carry flag being 0? Because it is. Okay? Well,
It's just that simple.
but in order for the carry flag to be a 1, there are certain requirements. Okay? You have to think about how to make the carry flag a 1. Why is the overflow flag a 1? Because the two input numbers are they negative or non-negative?
They're non-negative.
They are non-negative. If you look at the output here, if I use the 2's complement way of looking at things, is it negative or not?
It's
It
negative.
is negative. So I'm adding two non-negative numbers, and somehow the sum is negative, and that's why the sign does not make any sense. The overflow flag is a 1. But you can also use the equation that I just talked about in this class to look at the same bits. Okay? It's just that, you just focus on this column here. This is the most important column. Yep.
So the overflow means that when we take the two complement approach, we get a number that is contradicting the two other numbers. That's what you mean?
Say that again.
Okay. So when you have O equals 1, it means that it does not make sense adding two positive numbers and we get a negative number. Does it say that?
Does what say that? Sorry, I'm not understanding the question.
No, that's fine. Okay. Okay. So I was just saying about, okay, when we take the two complement approach, when you see, like as you said, we add the two positive numbers. So they start with the 0 in the
Well,
beginning.
let's take a look at the values that are being added here. What is the value represented by? Hello. Okay. What is the value represented by 0, 1, 1, 1 as a 4-bit number? It's 7, right? Because it's 1 plus 2 plus 4. What is 0, 0, 0, 1 representing? 1. 7 plus 1 in decimal is 8. Okay, so the result should be 8. This one can be representing 8 if we choose to look at numbers as unsigned. But when we talk about the sign flag, we have to be looking at things from the signed perspective. When you look at this number as a signed number, is it positive or negative? Is it non-negative or negative? Negative. It is negative. But what is the magnitude of being negative? It's negative 8. So we are saying 7 plus 1 equals negative 8, basically, using a 4-bit representation. And obviously the sign does not make any sense. So that's why this one does not make any sense. But you can look at this pattern here, and then you can look at the notes that we just wrote earlier today, and it's the same thing. If you look at the overflow flag, the most significant bit here is a 0, and the most significant bit here is a 0. So that means not A is a 1, not C is a 1 as well. The E is the sign flag of my result, which is a 1. So here we have 1 and 1 and 1, which is a 1. And that's why the overflow flag is also a 1. In other words, you can look at the bit pattern here and just extend it to look at any number of bits. Because for the most part, the least significant bits are not important. Okay. Yep.
Okay, when we have bigger numbers in hexadecimals, how do we represent not E or not A? Because it's easy to just show it in binary because it's 0 or 1.
Right.
But when we have bigger numbers, can you run one example with hexadecimal in the program?
Yes, I can. Okay, so you're basically talking about this in the case of A and then followed by 32 B's, right?
Yes.
Well, instead of looking at it this way, you can always look at it, using the subscript method. In other words, we can use A subscript 31 to mean bit 31 of the first number, A bracket 30 to represent bit 30 of the first number. So you just extend this all the way down to A bracket 0, which represents bit 0 of the first number. And then you say we add to the second number, in this case, B31, B30, yada, 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 all the way down to B bracket 0. Now, for the most part, we don't really care about the intermediate results. So these are all question marks because we don't really care. And this one is a question mark, except this one is our carry flag. And then we have a whole bunch of question marks here.
Wouldn't that first one be, that last question mark be a 0?
Yep, the last one should be a 0. Thank you. And then we have the result. The result, in this case, I would use C to represent it. So now we have C31 being bit 31 of the result, and then extend it all the way down to C bracket 0. So I'm just changing the notation to represent, the most significant bit. So in this representation, we can then define, C is still the same. Okay, C is just the carry of the overflow of the overall addition. But if you want to define Z, Z is basically the negation of, C31 or C30 or C29, etc. down to C bracket 0. So you can still look at things, the same way, except it is just a little bit lengthier now that we have 32 bits. But most of the reasoning you can apply to a 2-bit by 2-bit addition. You can still apply that to a 32-bit by 32-bit addition. The reasoning still extends. It's just that it's easier to look at the patterns when we have a 2-bit by 2-bit addition. Is that making any sense? It also makes it easy to exhaust all possible cases, because how many 2-bit by 2-bit addition can I have? 1, 2, 3, 4 bits. Okay, so 4 bits will only give you up to 16 combinations. And all those 16 combinations will exhaust every single possible combination of the sign, overflow, carry, and also what is the other one? Z flag, the 0 flag. But it gives you a better insight of why certain things are not possible. Okay, is that helping or not? Okay. I wouldn't do a 1-bit by 1-bit addition because in some cases it's not possible to generate a condition. So I would use at least 2-bit by 2-bit. Yep.
To find O, you said it equals A and C and not E. So when you say it equals A and C, you add A and C. And is that how you got the 1? Because you added
Where?
For your example.
This one here?
On the left hand side.
On the left hand side?
Yeah, for the.
For which flag?
For the O. Yeah,
The O flag?
Yes.
Well, there are 2 ways to look at the O flags. One is whether the sign of the result makes any sense, which is from the arithmetic perspective.
Yeah,
the other way to look at it is to look at it from the bitwise operation perspective. And the same equation applies, because if you look at the O flag equation, does it involve anything other than the most significant bits? Does the determination of the O flag depend on anything other than the most significant bits of the input and the output? Does not. Okay? So that means that equation applies to any width of addition. You can do 8-bit by 8-bit addition. You can do 16 by 16-bit addition. You can do 64-bit by 64-bit addition. But the overflow flag is still defined exactly the same way because it only depends on the most significant bits. Is that okay or not? Is it helping out a little bit? As I said, it is the carry flag that is actually the more kind of troublesome one. Because when can you generate an overflow? A carry as an overall addition. You have to kind of think about it. It has to do with there's a particular requirement of A, C, and only in certain conditions of A and C can the carry flag be a 1. Okay, I cannot spell it out, any more than that, but I'll leave you at that. In other words, the most significant bits are still important when it comes to the carry flag. Okay? And there's also a special relationship between the carry flag and the E flag here too. Okay, so you have to try out enough cases, then you can start to see a pattern.
Are they always going to be the opposite of each other? Can everyone be the same?
I cannot say it. Yep.
If we figure out one impossible combination, and we have a combination that requires even more flags,
Yes, if you have a sub-pattern that is not possible, then the overall pattern is not possible. So in that case, you can just say, see a earlier proof where the sub-pattern is proven to be impossible. Okay. Any other questions? No questions? Okay. So we'll go ahead and continue with the rest of the material. Where's my browser?
You have too many tabs open.
Oh, okay, it's right here. This class really tries to get you thinking like a processor. Everything is bitwise, bitwise, bitwise. Okay, so this time we're still in this particular slide. I think we're still talking about adding, and then we have all these flags determined. How do we see the flags? Add with carry is the last topic that we have not finished, as of last week. Okay, we have an add addition. We have an add instruction. Let us just kind of backtrack a little bit to the add instruction here. The add instruction is nothing exciting at all. Okay, it has two operands. And just like the move instruction, it has a source and a destination. In other words, in this case, if you look at add L, EAX, EBX, EAX is called the source operand, and EBX is called the destination operand. So what this instruction will do is to take the content of EAX, add it to the content of EBX, and then store the sum to EBX, because EBX is the destination operand. So normally when you do addition, there are three numbers, right? There's the two input numbers and the result. In this case, the second number and the result are the same. Okay, it will overwrite one of the operands to store the result. And that's it. That's the add long instruction. There's nothing really much else to it. It will allow all operand modes as in a move instruction. In other words, you can have any combination except for certain few ones. Okay? First of all, EAX can be an immediate operand, but this one cannot be. The second operand cannot be an immediate operand. Does it make sense?
Yeah.
Because you don't want to store the result of a calculation to an immediate operand. You cannot change the instruction on the fly to store the result. So the same restriction applies to the move instruction. The copy instruction has exactly the same restrictions. Other than that, the only other restriction is you can only have up to one operand being a memory operand. You cannot have two of both of these as memory operands. Only up to one can be a memory operand, and which is the same restriction as the move L instruction. That's it. Everything else goes. Okay. Any questions? Yep.
Why can't you have two memory operands?
It has to do with the internal architecture of the processor. When you look at the actual cycles of a processor, there's only one cycle dedicated to memory, to dealing with memory-related operands. When you only have one single operand, it can use that cycle to get the memory operand or to store the memory operand. But when you have two of them, it doesn't fit into the memory cycles anymore. In reality, you can have an instruction to do it, because the i386 instruction set, they're all basically emulated. In other words, inside every Pentium processor is a really high-end RISC processor trying to emulate the instructions of the i386 instruction set. So it is not really impossible for Intel to come up with a way to handle two memory operands. except the instruction itself, if you look at the binary code, there's no room left to specify the mode of 2 memory operands. So that's basically, historically speaking, we cannot handle it. It also is not needed because you can always break it up into 2 instructions instead of 1.
That's what I was.
Yep. Okay. Now the important part, the last sentence, which it doesn't seem important at all, okay? But this is actually very important because it changes the way you look at things. The add instruction does not choose the interpretation of the number, particularly to whether it is signed or not. When we add 2 binary numbers, we're just applying the 1 plus 1 is a 0 with a carry type of rules. There's no such thing as signed versus not signed when you are adding numbers or subtracting numbers, for that matter. Okay, so whether a number is signed or not is not up to the add instruction to determine. Okay, that's the add instruction. Now the add instruction can only handle up to 32 bits because we're dealing with the 386 instruction mode. If you want to use the 64-bit instruction set, then yes, you can add 64-bit numbers as well. But you still have a limit. Okay, the processor imposes an upper limit of how many bits you can add in one single instruction. What if 64-bit is no longer enough? What if I need an integer that has 128 bits?
You have a pretty big number there.
Hmm?
You have a pretty big number there.
Yes, but the national deficit is getting there too. I mean, we ran out of 32 bits a long time ago to represent the national deficit. Yep.
You'd pick an arbitrary precision number library and use that.
Yep, good luck doing that in assembly. Okay, so what do we do? Well, let's think about it. Let's think about it from the perspective of, let me find my text editor here. Let's say we can only do, yes, go ahead.
Can we make a processor that's like 128-bit processor? Just to handle an actual deficit?
Yes, we can have a new architecture just to deal with 128-bit additions and subtractions.
Use the technology.
Yep.
Windows 8 will run on soon-to-be-coming 128-bit processors, so he's not too far off.
Okay, well that's.
But I
that's
say
all
we
good.
take that always 0 carry bit and use the carry from our previous operation and insert it there
Exactly.
instead of just making it always be 0.
Exactly. So what Christ just said is exactly the solution. It's not just for extending a 32-bit architecture to handle 64 bits. It's also used to extend an 8-bit architecture to handle 16 bits, 32 bits, 64 bits, and so on. And it's easy. It's really easy. So what we want to do is to take a look at 4-bit by 4-bit addition. And then we will ask ourselves, how can we handle it using 2-bit by 2-bit addition instructions? Okay, so we are shrinking the sizes down to something that we can actually see very easily. The first number is, let's see, I'm trying to figure out the best way to represent this. Okay, so we'll just use ABCD as the first number. That's the bit pattern of the input. And then we have D, E, F, G as the second number. I still reserve one row for the carry flags because it is important at a certain point. And the answer is going to be G, H, I, J, K. And then we'll have L. I've used uppercase L because the lowercase L looks like a 1. Yep.
You put 2 D's on there.
I put 2 D's? Okay. E, F, G, H, I, J, K, L. Is that L okay? I mean, in
Use
this
a semicolon.
font,
Use a semicolon.
K, L, M. Okay, we'll skip L. And then we have N here. How's that? It doesn't matter. I mean, it's just, we just need a symbol to represent each and every bit that we have to deal with. Okay. So this is a regular 4x4, 4-bit by 4-bit addition. What if I tell you you can only add 2 bits at a time?
Okay.
Okay. So now the question is, how can we break this up into 2-bit by 2-bit addition? That's the question. Okay, so we'll separate it now. Okay, I'm just adding one additional column, like that. Okay? And I would just say, the addition of bits CD and GH will be handled by one instruction, and it will use another instruction to deal with the adding of AB and EF. Can we do that? That's the question. Why can't we do it that way?
Because normally we have ABCD, and it's like AB00 plus 00CD would give us ABCD.
Well, not quite. The reason is because this one cannot be a 0. We don't want it to be a 0. This guy has to be the carry from the first addition, from the one on the right-hand side. So that means the carry flag in between, which is this guy here, I'll give you another name, OP, we'll call this bit P, has to appear to be here. Okay? In other words, I can separate, one single addition into two addition instructions. The first one is just a regular add because I have the fixed 0 as the first carry flag. It's not a problem. The second addition, on the other hand, cannot use a flat 0 here because there may be a carry generated by adding C and G. Does that make any sense?
So what do you use if you can't use 0?
Well, there are several ways to do it. But since we have not talked about conditional branches, the only way to do it is to use another addition instruction, which is called add with carry. Okay, that's the add with carry instruction. Yep.
Speaking of add with carry, can we do attendance now?
Attendance? I forgot to bring my roll sheet, so we are good. It's a good time to talk about the questions on Thursday. Oh, but we haven't scheduled our exam yet, have we?
No.
How about
Okay,
Thursday?
well, since we are not done with this topic yet.
How about Thursday?
Thursday?
Yeah.
For exam?
No.
Pop exam? No, I don't think I'll do pop exam. Okay, so what we'll do is, so I'll explain what is add with carry. A regular add instruction uses a constant of 0 as the carry bit to bit 0. In other words, in our picture, we are looking at this 0 here. That's always there because there's no carry from a prior addition. So the sum is really just, but when we want to extend an addition instruction, we have to take that into consideration. So this add instruction here is going to add just like normal, but it will also use the carry flag as a third operand. This becomes EAX plus EBX plus the carry flag to become the result. The result will still be stored in EBX. Is that making any sense? Okay, so add with carry is basically the same as a normal add instruction, except there's a third implied operand. The third implied operand is the carry flag itself. Now the carry flag seems like it's just a flag. Can we add a flag to a result? The answer is yes, because the carry flag is either a 0 or 1, and we can certainly add a 0 or 1 to a number. Yep.
So our carry flag is dependent on the previous operation?
Yes, that's exactly right. Yep, that is exactly right. Okay. Yep.
Are there any operations that reset that carry flag with a guaranteed known value? Are there any operations that reset that carry flag with a guaranteed known value such that you can start an operation with an add CL?
Oh, that's
rather
easy.
than having
You can always load 0 into EAX and add EAX to EAX. That will clear the 0 flag for sure.
Ah, excellent.
There is a single instruction to clear the carry flag too. But even with the instructions that we know already, we can reset it. Sure.
Okay.
It's just
that's
a
good
little
to
more
know.
cumbersome to do it that way. Okay. So let's go ahead and use an example. Okay. The best thing to illustrate this kind of concept is to use an example. Today is the 22nd. And I'll call this program add with carry, just as the name implies. And I'll use the comment to illustrate what I want to do. What is the largest number that we can represent in 8 bits?
111.
Unsigned.
Oh, 1 is 0, 1, 1, 1.
No, unsigned.
Oh, one.
As an unsigned interpretation, what does 1111 represent? 255. So every time we have to roll off 255, we have to use another byte to do it. Does it make sense? Okay.
That would be FF.
That will be in hexadecimal FF.
Oh.
Yes. Okay, so what we want to do is to do something like this. I will shrink everything down to 8-bit levels. I will first move byte. Okay, we'll put a 255 into an 8-bit register. There are plenty of 8-bit registers to choose from. AL is an 8-bit register. And then we'll say add byte 1 to AL. Well, do we know what is the result? What is the result of this addition? AL will end up with a 0 because, and the carry flag will be a 1. So if I want the result to be stored in 2 bytes, okay, what do I need to do? I need to, the second addition, okay, is going to be an add with carry instruction, byte wide, and I can just add something else to the other byte.
-0AH.
Okay, let me, let's see. 255. This one. Okay. We want to compute 255. It doesn't have to be +1. Let's say we want +12 to it. Okay. And store the result in 16 bits. Okay, that's what we want to do because we know 8-bit is not enough to store the result. We use AX as the first number. We use BX as the second number. But we can only use 8-bit add instructions. Okay, so here we have a problem because we have these restrictions. So I'm going to start from scratch, just to show you how to do all this. It's not difficult to initialize the registers, is it? Because the first one is just move W, 16-bit move or copy 255 to AX. The second one is move word 12 to BX. That will initialize the 2 registers. I don't have any restrictions as far as initializing the registers are concerned. But when I add, I can only use add byte or add with carry byte. So the question now is, how do we do it? How do we do that? Well, first of all, you have to know what is AL and AH, what is BL and BH. AX has 2 components. This is AX here. AX has AL as the least significant component, has AH as the most significant component. BX is about the same thing. We have BL and then BH. Is that okay? And we want to do an addition of these 2. I can use one addition to add the AL and the BL and store the result into BL. Is that okay? That's just an add B instruction or add byte instruction. The add byte instruction will give me a carry flag that I cannot store in 8 bits. That carry will be put into here. So the second add instruction will add AH to BH, but I also want to add the carry as a part of the addition. Is that making any sense? Okay. So to translate this picture into instructions, that means the first instruction is just add B or add byte. We're adding AL to BL. We always go from the least significant part to the most significant part because the carry only propagates from the least significant side to the more significant side. And then the second instruction is add with carry byte, AH, BH. Okay? So I'm suspecting that at this point we will have the correct result. So we'll say check point, and then we'll finish up the rest of the program. The rest of the program is just the usual exit pattern, which we cannot explain at this point. So here's my program. Are there any questions about the program itself? Nope. Okay. I'll do one more thing. I'll just do a move L $1 to EAX,
You
and
said
a move L.
1 and drew 0.
Sorry?
You said 1 and put a 0.
Sorry?
You said $1 and put $0 on the
Oh.
first EAX.
Oh, that should be a 1. It should have been a 1. I said it wrong.
You
The
said
first line.
1 up top. Very
This
top.
one here?
You said 1 and put a 0.
Oh, okay. I want to put a 0. Sorry.
Okay.
See, I'm inherently confusing.
Never trust tech.
O, EDC.S, LD-O, ADC, ADC.O. Oh, okay, I forgot one thing. I forgot to say text, global, start, underscore start. Okay, there we go. Now this is really just a warning. What this message is saying is it is defaulting the beginning to where the first instruction is. In other words, normally you can write a program this long and you can specify any place within the program as the starting point, because the starting point has a special label called underscore start. When I wrote this program the first time, I forgot to define the label underscore start, and as a result, the linker said, oh, it's okay, I'll just assume the first instruction is the starting point of the entire program. That may work sometime, but it may not work at other times. So it's always a better thing to define the underscore start. E, GDB, GDC. I will go ahead and list the program.
EIEIO.
I have to display the flags. It's okay, we'll display the flags in another way. Okay, just not as convenient because I don't have .gdb in it in this folder. Okay, I'm running my program, and I will single step through the first 2 instructions. I look at EAX, it is 0. I look at EBX, it is 0. Now the reason why I zero out both EAX and EBX is because I cannot do this. I cannot say IRAX. Oh, it does.
You can now.
It does. It did not do that before. Okay, well, so the first 2 instructions are somewhat pointless now. Okay.
You're
and
showing
now,
initialization. That's always good.
yeah. And now we initialize the AX and we initialize BX. Okay, always good to double check. AX is 255 and BX is 12. So we got everything ready to go. Okay. You look at this bit pattern here. What do you think is the result after the add B instruction? After this instruction here. First of all, what do you think will end up in BL after this instruction?
11.
It will be 11 in decimal or B, 0B in hexadecimal. Okay? What about the carry flag? Would the carry flag be cleared or would it be set?
Set.
It should be set because
There's a carry.
there's a carry from the most significant bit. Okay.
What about
So-
the O flag? What about the O flag?
What about the O flag? That's a good question. What about the O flag? Do you think the overflow flag is going to be cleared or do you think it will be set? It'll be
Cleared.
cleared for sure. The overflow flag is going to be cleared for sure because the sign flags of the 2 inputs are different. When you add a negative number to a non-negative number, the result can be either way. So there's no way for the result to make no sense. The sign of the result cannot make no sense. It always has to make sense when one number is negative and the other one is non-negative and you're adding those 2. Okay. So we single step and then we take a look at the result. So let's see if BL can be displayed by itself, and yes. Okay. Now we also want to check the carry flag, and I did not put in .gdb in it. In other words, flags as a command is not defined because I have not defined it yet. It is defined in .gdb in it. So what do we need to do is we can look at the register called eFlags. Okay, there is a register called eFlags, and that's the register that is storing all the flags. So in this case, it's showing us that this carry flag is in fact set.
What's A and I?
Don't know. I think the I flag is the interrupt flag, but I'm not sure about the A flag. Okay. Are there any questions at this point? Everything is going the way it is supposed to. Okay? So now we look at the second instruction. The second instruction that we want to use, or the second add instruction, is adding AH to BH. It helps to take a look at what is AH first, and take a look at what is BH. Ah, that's easy. 0 plus 0 is 0, right? Except it is not a regular add instruction. This is add with carry. So what we are doing is we are adding AH and BH and the carry flag. Okay, those are the three components of this addition, and the result is going to be stored in BH. Okay, so what do you think is going to happen after this instruction? What is BH at this point? It should be 0, 1 in hexadecimal, right? IRBH, sure enough, it is 1. What about the carry flag?
Should not be set.
Should be cleared, should be 0, because we are adding 0 to 0 to 1, which does not trigger the carry flag for an 8-bit add instruction. Okay. What about if I look at BX? What should I see here?
2.
We were adding 255 to 12.
267.
Should be 267.
Darn, I was wrong. It was 10.
In other words, we successfully added a 16-bit number to another 16-bit number, but only using 8-bit additions in the process. Is that okay? And you can do the same thing, not okay?
Not okay. Bad math, man.
But what if this is an 8-bit processor?
Then we need a better processor.
What if I don't have money for a better processor?
Someone in management needs to be fired. Someone in management needs to be fired.
What if this is Micro Mouse? This is a robot that has a budget of $200, and I have to use a cheap, inexpensive processor.
You need to raise your budget.
No, you have to use the add with carry instruction. That's why we have the add with carry instruction. How many people think the add with carry instruction, or at least the concept of the add with carry instruction, is very important? Okay, because it allows a smaller architecture, say 8 or 16-bit, to actually perform, addition and subtraction. There's a matching instruction for subtraction, and you can extend it to 32, 64, any width that you want. Okay, it will take additional cycles, it will take additional time, but the approach is easy. Okay, the first one has to be a regular add, and then you just use add with carry for all the more significant bytes, or the more significant words, and so on. Now, when Motorola changed the 68,000 architecture to become the code file architecture, they were basically taking a CISP architecture and trying to turn it into a RISC architecture. One of the instructions that they took out was, guess what? Add with carry. Because whoever was doing the job did not think there's any application of add with carry, but in reality, it is a very, very useful instruction. Are you guys convinced that it is a very useful instruction? Okay. So let's go back to this program. And I will not make this a homework assignment, but I will just go ahead and challenge you guys and change this add with carry to add regular add. Just change it to a regular add instruction here, and you will see the result is wrong. Okay? But I want you to predict how wrong it is going to be. Okay? Why is it wrong, and how off the result is going to be? It's not off by 1. Well, I take it back. It is off by 1 from the perspective of the more significant byte. But when you look at the entire 16-bit pattern, it's not off by 1 because it's off by 256. Exactly.
It's going to be 11.
Okay, so I'll leave this one up to you guys, to actually run it and see the result and see that, okay, so if I don't use add with carry, the result is wrong, and this is how it will be wrong. Okay, any questions about add and add with carry? Nope, no questions. Okay. So we are done with addition, and we are now moving on to subtraction. Oh boy. Wow.
Can't we just add negative numbers?
You cannot negate numbers yet. So if I give you 4 and 5, there's no way for you to compute the negation of 5 to emulate the result of subtraction yet. So we don't have all the tools needed to really do any subtraction.
Okay.
Because you would need 2's complement, or at least 1's complement, to do the 2's complement. But we don't. I haven't talked about 1's complement yet, so we cannot do it just yet. So this is the slide that talks about subtraction. Very exciting stuff. Subtraction rules, we have done this already. Do you guys remember this? Okay. 0 minus 0 is 0 with no borrow, or a borrow of 0 if you will. 1 minus 0 is 1 with a borrow of 0. 0 minus 1 is the only time when we have a non-zero borrow, so we have to borrow from the more significant digit. In other words, this is basically 0 minus 1 equals 9 with a borrow in base 10. Same thing. And the last one is trivial. 1 minus 1 is 0, regardless of the base, with no borrow. So do we have any questions about the rules of subtraction? They are just as easy as addition, really. And in this case, I use these really obscure symbols to define the result and also the borrow. So the result, okay, if you look at R is, okay, what is R? Let's take a look at the previous slide. I'm just going to open it as a new window. Where is it? That's not it. Oh, I clicked the wrong link. That's fine. So what we do is we'll display these side by side. Okay. This is the result. 0 minus 0 has a result of 0. 1 minus 0 has a result of 0. 0 minus 1 has a result of 1. Oops, sorry, I said it wrong. 1 minus 0 has a result of 1. 0 minus 1 has a result of 1. 1 minus 1 has a result of 0. So if I want to use bitwise operation, how can I express the result, the 0, 1, 1, and 0, in terms of the input, which is 0 and 1s?
If the inputs are the same as 0?
If the inputs are the same, the result is 0. If the inputs are different, then the result is a 1. Does that make any sense? And the way to express it is exclusive OR. But since exclusive OR is not a simple gate, it's not a simple gate, you will just use this expression to do it. Can everybody see how xy bar plus x bar y is implementing the same thing as exclusive OR? Okay, the first one handles the case when x is 1 and y is 0. X is 1, y is 0, but y bar is not y is also 1. 1 and 1 is 1, we don't care about the other side. The second case takes care of the case when x is 0 and y is 1. Because when x is 0, not x is 1, y is 1 already, 1 and 1 is 1, and this conjunction is a 1, and the whole result is going to be a 1. Is that making any sense? Remember, what you see as multiplication is actually conjunction, or and. What you see as addition is actually disjunction, or the OR operator. What about the borrow operation? The borrow operation is 1 if and only if the first number gives me a 0 and the second number gives me a 1. That's the only time when you need to borrow from the next digit. So that's why when we want to define the borrow function, it is just x bar y. Because x bar and y, or not x and y, will only be true, or 1, if and only if x itself is a 0 and y itself is a 1. That's the only time when x bar y can be a 1. Is that doing okay so far? Okay. In other words, what we have done at this point is we have changed the interpretation from the previous slide from the arithmetic perspective now to the Boolean logic perspective, which is a very significant change of perspectives. Because, okay, let me just show the other slide so that we can compare the two. What is the other one? The rules. Okay? When we talk about the result and a borrow, the concept of a borrow is arithmetic. Okay? I don't have enough values on this column. I'll borrow one from the more significant digit. It is from an arithmetic perspective. But when on this slide on 2.2, we are looking at things from a strictly gate or logic perspective, because all the operations are defined by what? Conjunction and, disjunction or, and negation not. So that's a very significant transition, because now things can be done by gates, and anything that can be done by logic gates can be done on a processor using transistors. Can everybody see the importance of this slide here? Even though it seems like we're still doing the same thing as the previous slide, but now we're translating everything to the gate level. And this is basically the same thing as in the addition slide. In other words, if we want to use D as the difference or the result of the subtraction, so here, okay, let me just start from the beginning. Let X be a number, okay, and Y be a number, and they're both n-bit numbers. We use the representation X subscript I to denote bit I of X. So X is a number with a certain number of bits n, and X and Y also has n bits. The result or the difference is denoted by D, which also has the same width. It also has n bits. Okay? So what we want to do is to figure out how do we express the result of X minus Y. When you look at bit 0, it is the result of X and Y, or the bit 0 of X minus bit 0 of Y, without anything else. Because the borrow from the previous digit is a 0. In other words, if I want to use an example, it's best to use the text editor here. Okay, let's take a look at one example. Let's say 0, 1, 0, 0 minus, we'll just make it really simple like this. Okay? We have done subtraction already, so this is not the first time we have done anything like this. It's just that I want to make it very clear how we get to the result. Okay, this is what we want to calculate in base 2. What is the result of 0 minus 1? Okay, it is a 1. And what is the result of the difference for the same bit position? It's also a 1, because the borrow from the previous digit has to be a 0. This is the least significant bit already. And that's why I say D0, which is bit 0 of the result, is just the result of subtracting Y from X, the first bit 0. Is that making any sense? Okay. Now, when we look at the second bit, now we have this intermediate bit here. Well, what we want to do is to get down to here. What is this? Okay, so it doesn't really, it's not as easy to express it like this now. So I will have to go back to A, B, C, D minus E, F, G, H. And I, J, K, L. M and O, that's a 0. And then we have P, Q, R, S, and we'll call this T. Okay. What is S? Well, bit S is the same as bit L. Bit L is R, D, H. It is the result of subtracting bit H from bit D. What is K? K is easy. Okay, K is the result of subtracting bit C, subtracting G from C. And the same thing with J, that's an easy one because it is just subtracting bit F from B. And the same thing for I, bit I is the result of subtracting E from A. Are we doing okay so far using the notation that we have talked about so far? Okay, but O is a little bit different. Okay, O is the borrow. And there are two ways to generate that borrow. I could generate a borrow when I have bit H minus bit D. I can have another borrow. Can I have another borrow?
No.
Yes, I can. Okay, this one only has one single source of a borrow, which is the subtraction of h from d. So b, and this will be dh, like that. Does that make any sense? Okay. What about r? R is the result of subtracting KO, okay? But since we know what K is, we can expand it, right? We can just replace K with the definite, with the RCG and O. But since we also know what O is, we can say this is R of CG, and then O is BDH. Is that making any sense? Okay. Let's work out what is N. What is N? In the simplest case, what is N? There are two ways to generate N. I can have a borrow when I subtract G from C. That can generate a borrow. When I subtract O from K, that can also generate a borrow. So there are two sources to generate a borrow, which means it is a disjunction of those two borrow flags. Okay? So N is BCG or BKO. Okay? Then you look at CG cannot be simplified anymore because that's the input. You cannot simplify the input. But K can be simplified because K is this mess here. So you replace K by RCG. We also know what O is. O is BDH. Copy and paste it here, and we are done. Are we doing okay so far with this? So far, how many bits have we handled? 3 bits. Okay. Well, almost 3 because we haven't handled Q yet. Yep.
I mean, can you go over again? What's the K and R and what those mean?
Sorry?
With the K, you go to R and then CK and CQ.
Okay, K is here.
Right.
K was first defined up here. It is RCG because it is the result of subtracting bit G from bit C.
Okay, all right.
Okay? And O, which is this guy here, is the borrow from the least significant bit subtraction. In other words, when we subtract H from D, O is the borrow of that subtraction. And that's why O is BDH because it is the borrow of subtracting H from D. Is that okay?
Yes, no.
Okay. So this is just a game of expansion. Okay? If we keep expanding it, what is Q? Okay, let's do it the easy way first. Q, if we do it the easy way, is RJN, right? But what is J? J is this bunch of stuff here. And what is N? Oh, N is not that easy anymore, is it? That's our N here. Can you guys see though how this can get a little bit more difficult in the next bit? Can you imagine the equation for bit 31 of a 32-bit by 32-bit subtraction? It's just going to be long, but there's a mechanical way to do it. This is just mechanical expansion, right? And what is the best mechanism to do mechanical expansion like this? It's something that you should know already, but I'm not sure whether they talk about it in that class.
Recursion.
You can do it by recursion, but this does not need to be programmed at all. Come on. Drum roll.
A processor.
There's a processor. Yes, that's the name. That's a part of the name of the tool that you can use. Yes. Can anyone say CPP or the C preprocessor? Macros. Macros in C can do this because they're all text replacements. No,
We're not going to write this in C.
Okay, let's keep doing. Okay, because by the time it gets painful, I think most people will realize how to do it.
We all realize how to do it.
What is M? Now, by definition, what is M? M is B D,
J and N.
oh, BF, or BJN. Is that right?
Yeah.
Yep. Okay. So when you feed this to a C preprocessor, the and you define K as a macro itself, it will expand K. Whoops. If you define K itself as a macro, it will keep expanding it until it cannot expand anymore. Okay. So the preprocessor can actually handle this, but if we have to handle it by hand, it's going to be quite painful because it is just BF. And J is this guy here, and N is this guy here. Yep.
When we're writing this in our own assembly files, can we use the C preprocessor so we don't have to copy and paste like you are?
Sure.
Can you show us how to do that now, please?
You just when you just pound define everything. Everything is a pound define.
In assembly?
Yes, you can. You just have to make your file end with a uppercase S extension instead of a lowercase s extension. Then you can use GCC to process it, and GCC will feed it through the preprocessor first. So you can use pound include, pound if, def, pound if, pound else, pound and if, and all those macros can also be used in assembly language programming.
Awesome, thank you.
It is awesome, isn't it? Okay, what is P? By definition, what is P? P is by definition is just RIM. Because P is here, it is the result of subtracting bit M from bit I. And the next question is, what is I? Oh, I is easy, but M is not. It's easy when you can do a copy and paste. It's not so easy if you have to do it by hand. Okay, and finally, what is T? The final borrow.
Carry from AE or IM.
Okay, is BAE plus BIM. And BAE cannot be simplified because those are two input bits. But I can be expanded. I is RAE, and M is a big mess. Just like that. Now I want to write everything using conjunction, disjunction, and negation.
Have fun with that.
Well, that's the kind of fun that that you get when you write when you try to write the logic of a processor. And guess what? You can leave it just like this and leave it up to the Verilog or VHDL simulator to figure out the rest. So all you have to do is to express the relationship between the bits, and how the bits will be implemented by logical operations can be handled by the VHDL or the HDL stands for Hardware Description Language. So there's a particular program, quote-unquote, programming language to describe hardware. Yep.
So why do we expand it all like that again instead of just relying on each previous operation to have been completed, since none of them is
Very
useful
good
without the
question.
ones before?
So I'm pretty sure you're asking because you want to prompt me to answer that question. You already know the answer. Okay.
No.
So but let me repeat that question. The question is, why do we have to expand it like this? In other words, can't we just leave it as BIM, and M is defined like this, N is defined like this, and OK is defined like this, O is defined like this. In other words, we have to figure out what is, we have to figure out these, values in this order. If we evaluate things in this order, we don't have to mess with, like huge long equations like that. Is that your question? Does everybody understand the question itself? Okay, why do we have to keep expanding everything until it cannot be expanded anymore, and everything is expressed in input bits? If you look at this equation here, all the letters that we are using are the input bits. They're all, well, I scrolled it off the screen already, but they're all bits of the input. Why do we want to do it this way? Yep.
Because it will take more time?
Exactly, because the other way takes more time. If you do it this way and you simplify the equations, then you can minimize the propagational delay. It will give you the result in the shortest amount of time.
So basically, you just figure it out a little bit more, so it takes less time, so it doesn't have to figure it out by itself.
Yes, but it will use up more hardware. In other words, you will be doing some calculations redundantly. Okay, but it will give you a better result. It will give you the result faster because it is taking all the inputs directly. Okay, but you have to do the simplification. If you don't do the simplification, it's the same as before. But if you do the simplification, then it can be a lot faster. The simplification can also be done by automatically. So there are programs out there that can simplify Boolean equations so that you have the least number of operations that you need. So do you guys want to stick with programming or do you want to do some hardware stuff?
Let's stick with programming for tonight.
Okay.
Become farmer.
Doesn't sound
so we're
unfun,
almost,
just
well, we
tedious.
are kind of out of time today, so I cannot talk about the 4 flags, but in the context of subtraction. So what you guys need to do before Thursday is to read all the way up to here. Okay, finish this entire module, at least finish reading it. You may not understand everything, that's okay. Write it down on a piece of paper and say, okay, this part I don't quite understand, and now you can ask it during the class. But read this entire module because we want to understand how this Z, C, S, O, and L flag this time apply to subtraction. Subtraction is a whole lot more fun than addition.
Fun, huh?
Because you can compare. Because it can also be used for comparison. And that's why it is so much
Is the
more
mic
useful.
off yet?
The mic is not off.
Okay, that's all I'm waiting for to ambush you.
Maybe I should keep it going on.